Yeah,
Okay.
so I think everybody knows me from the previous lecture. All right. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh.
Waalaikumsalam
Waalaikumsalam
warahmatullahi wabarakatuh.
wabarakatuh.
So let me remind you about the series of lecture. So as you know, in part one of my lecture, I introduced I just remind you some noun groups and introduce some probability and graphs associated uh, to groups and rings and so on. In the second part, which we are in the second lecture of the second part, I would like to continue about the spectral graph theory in algebraic graphs. Uh, in the last week, just let me remind you very quickly, uh, I introduced general inverse, and so the main point was that I uh, introduced some matrices associated to a graph. The important ones uh, were the incidence matrix, right? The incidence matrix and the path matrix. And so let me remind you again. So the first matrix which I introduced was incidence matrix for directed graph. Of course, we are all talking about simple graph, so we don't have any loop and any multiple edges. And then I introduced one special case of the inside this matrix, which was one incidence matrix. So this was the second matrix which I introduced, right? And the third one, which is one of important matrix, was adjacency matrix of a graph. This is one of very important matrix associated to a graph, and as you know, this is n times n matrix, which uh, uh, which is indexed by rows and columns by vertices, and if we have an edge between two vertices I and j, then we will put 1, otherwise we can put 0. The This is the spectrum for some important cases of graphs, some noun graphs, right? So let me pass this one. And here are some just a Cartesian product for some examples, right? And here is about the eigenvalues for the disjoint union of two matrices. And here are some examples on eigenvalues and a spectrum in some algebraic graphs. This is example about conjugate graph of symmetric group S3, and similarly for the symmetric group S4. So this was the project number 3 for the spectrum of conjugate graph in symmetric group Sn for any n bigger than or equal to 3. Another example about the dihedral group, conjugate graph of dihedral group in general case for n is odd and even, right? And that's the some research problem. Now, right, so this is for dihedral group of order 8 adjacency matrix. And that's some research problem for the spectrum of non-commuting graph of dihedral group in general case, or general quaternion group, symmetric group, and alternative group. This is another example about stereo for coprime graph. That's the adjacency matrix for coprime graph of S3, and that's the for dihedral group. Now, I think we mentioned until here. So the project number 4, as I mentioned at the beginning of my lecture, in the lecture 1, I will introduce some project. So anybody who are interested to join to this project, you can contact Dr. Yeni, and she will manage for just creating a group research to deal with any of these projects. So the project number 4 is that determine the spectrum, means the, the set of all eigenvalues of coprime graph of dihedral group in general case, dihedral group of order 2 times n for any n bigger than or equal to 3. This is the project number 4. Now, today I will just continue about the just some other matrices associated to a graph, and also some related topic to these matrices. One of them, which is very important for the adjacency matrix, is the energy of a graph. So actually, the energy of a graph coming from chemistry, it has many applications in chemistry, but just we can give some of graphs coming from chemistry. Now, the energy of a graph in graph theory defined as the following. Suppose that gamma is a graph with vertex set. We have n vertices, 1 to n, and m edges, E1, E2, and En. So if A of gamma is the adjacency matrix of gamma, and lambda 1, lambda 2, lambda n, or eigenvalues of the adjacency matrix, then the energy of a graph gamma we may denote by E of gamma, just a small e, because the capital E we will denote for the edge set. So we use the just a small letter E of gamma for the energy. So the energy of a graph gamma is the sum of absolute values of all eigenvalues of adjacency matrix. So the energy of graph gamma is the sum of all absolute values of lambda I from I is 1 to n. That's the definition of energy. Of course, we will have some other kinds of energy, which I will give more details later in this lecture. Let me give example for the adjacency for the energy. So assume that a bipartite graph K23 is the complete bipartite graph, right? So we have two vertices in the first set, right? And three vertices, 3, 4, 5 for the second set. And we have edge from any vertex in the first set to the any vertices in the second set. So we will have, 6 edges here. The adjacency matrix of complete graph K23 is the following. So we have a block of 4 zeros on the top left, and the block of 6 ones on top right, and similarly on the below left, we have a block of 3 times 2 ones, and on the below right, we will have block of 3 times 3 zeros. We have zeros on the just top left and below right, because we don't have any edge in the sets consisting of vertices 1 and 2, right? And similarly, for 3, 4, 5, we don't have any edges also here. So we will have 2 zero blocks here. Now, the eigenvalues for the adjacency matrix, we have 3 zeros, and so 2 non-zero eigenvalues. We have minus root 6 and plus root 6. So the energy of this graph is the sum of all eigenvalues, and that's equal to 2 times root 6. That's the energy of complete graph K2. We may just use the eigenvalues and also sometimes energy to give a relation between eigenvalues and the chromatic number, right? This is a lower bound for the chromatic number. Chromatic number means we may have K coloring. It means that we may give a color to each vertex with these conditions that we don't have the same color for adjacent vertices, right? So, the lower bound for the chromatic number is 1 minus lambda 1 is the biggest eigenvalues, and lambda n is the smallest eigenvalues. And you know that since the sum of eigenvalues of the adjacency matrix is 0, so the lambda 1 must be positive and lambda n is negative. If all eigenvalues are positive, so the sum of them is not 0. And similarly, if they are all negative, so we should have some positive and some negative eigenvalues. So lambda 1 is positive and lambda n is negative. So it means that 1 minus lambda 1 over lambda n is a positive number. Another theorem is that if we have a graph gamma with n vertices, right? So the energy of this graph is, we have two cases. If the energy is rational or irrational. If the energy of a if of a graph is rational, then it must be an even integer. Otherwise, it must be irrational uh, integer. So let me give the energy for non-committing graph in some for some groups. Here is a table about the adjacency, about the eigenvalues of the adjacency matrix of non-committing graph and the energy. So I consider for dihedral group. So if you look at here, for dihedral group of order 6, we have 6 for dihedral group of order 6, we have 5 eigenvalues, because the vertex set for dihedral group of order 6 is the non-central elements, right? Because the center is trivial, so we remove identity from the set of elements of dihedral group of order 6. So we have 5 vertices. So the adjacency matrix is 5 times 5, and we have 5 eigenvalues. So we have 1, 0, 2, -1, and 1 eigenvalue 1 plus root 7 and 1 minus root 7. If we add the eigenvalues of the absolute values of these eigenvalues, we get the energy 2 plus 2 root 7. For dihedral group of order 8, we have 6 vertices, because the center is identity and a square, so we have 6 vertices. So the adjacency matrix is 6 times 6, and the eigenvalues, we have 3 zeros, right? 1 4, 1 eigenvalue 4, and 2 eigenvalues -2, and the energy is 8. And similarly, you can see for dihedral group of order 10, of order 12, and order 16. That's the energy. Now, it's interesting to see that what we can say about the energy for dihedral group of order, for non-committing graph of dihedral group of order 2 times n in general case. So here is the energy for the adjacency matrix of, let me give this convention. When we are talking about energy means the sum of absolute values of all eigenvalues of adjacency matrix. Because we will introduce some more energies, so energy without anything is the sum of all eigenvalues, the absolute values of eigenvalues. So here is the energy for non-committing graph of dihedral group of order 2 times n. You know, we have 2 cases for n is odd and n is even. And also here another results about the eigenvalues for non-committing graph of dihedral of direct product of 2 groups. So if G is non-abelian and H is abelian, so H is non-abelian and H is abelian, so the energy of direct product of G and H is the order of H times the energy of non-committing graph of G, right? For example, for dihedral group of order 8, which is non-abelian group, and cyclic group of order 8. cyclic group is abelian. So the energy of non-commuting graph of dihedral group of direct product of dihedral group of order 8 and cyclic group of order 8 is the order of cyclic group of order 8, which is 8, times the energy of non-commuting graph of group of order 8, which is also 8. So 8 times 8 is 64. Now here is an exercise to see that what's the energy for non-commuting graph of direct product of two copies of dihedral group of order 8. You know, here we cannot use the above theorem because here dihedral group of order 8 is non-abelian, and also the second dihedral group of order 8 is non-abelian. So just the exercise says that what's the energy for the non-commuting graph of direct product of dihedral group of order 8, two copies of dihedral group of order 8. And here is a research problem. So what we can, if G is non-abelian finite group, so what we can say about the energy for non-commuting graph of direct product of two copies or maybe three copies or in general n copies of G. Here is energy of some more algebraic graphs. So as you can see, here is the energy for conjugate graph of symmetric group S3, right? And also energy for conjugate graph of S4, conjugate graph of dihedral group of order 2 times n. You know, this is in general for, of course, n is an odd number. And here is, again, energy for conjugate graph of dihedral group of order 2 times n for n is even. Now, number 5 is the energy for coprime graph of S3. Here, you know, it's 7.533. And energy for coprime graph of dihedral group of order 2 times p, for p is an odd prime number. Right. Now, I'm going to continue introducing matrices associated to a graph. We are going to define the Laplacian matrix. Laplacian matrix is also one of important matrix, which is associated to a graph. So suppose that gamma is a graph with vertex set 1 to up to n. So we have n vertices and m edges. The Laplacian matrix of gamma we may denote by L of gamma is n times n matrix, and we may denote and we can define as the following. So first of all, the rows are and columns of the Laplacian matrix are indexed by the vertices. So we have n vertices. So the Laplacian matrix is n times n matrix. Now consider two vertices, I and j. So we have two cases. If I is not equal to j, so the adjacency matrix, let me define here. So as I mentioned, so the Laplacian matrix of a graph gamma is n times n matrix. Now look at row I and column J. So the entry Lij, we have three cases. If I is equal to J, it means on the diagonal. So on the diagonal, if I is equal to J, so Lii is the degree of vertex I. Now, if I is not equal to J, right? So we have two cases. The first case is that if I is adjacent to J, so in this case, we will put -1 for the entry. And if I is not adjacent to J, we can put 0. So that's the definition of Laplacian matrix. Let me give example here. So suppose that gamma is the following graph. So we have 6 vertices here. You can see the degree of any vertex. Degree of vertex 1 is 3 because we have 3 edges just involving vertex 1. Degree of vertex 2 is 3. Degree of vertex 3 is 2. And vertex 4 degree is 2. Degree of vertex 5 is 5. And degree of vertex 6 is 1, right? Now, look at here. On the diagonal is the degree of vertex. So 3 is for vertex 1 on the diagonal. So the entry 1 is 3 because degree of 1 is 3. And the second 3 for degree of vertex 2. And 2 for the degree of vertex 3, the second 2 for the degree of vertex 4, and 5 is the degree of vertex 5, and 1 is for the degree of vertex 6. Now look at other entries. For example, look at entry 2 and 3. So 2 and 3. 2 and 3. We have edge between 2 and 3. So 2 is adjacent to 3. So we have to put -1. And you can see here, 2, 3 is -1. How about 2, 4? 2, 4 is 0. 2, 4 is 0. You can see there is no edge between 2 and 4. So the entry related to 2 and 4 is 0. You can see all columns here. So one of important properties of the Laplacian matrix is that if you add this, if you add all entries in each row and each column, it's 0. So look at the row number 1. 3 plus -1 plus -1 plus -1 is 0. It is 0. Look at column 4. Column 4 is -1 plus 2 plus -1 is 0. So the sum of all values in each row and each column are 0. This is the Laplacian matrix of complete graph Kn. So we have n vertices. The Laplacian matrix is n times n. Now look at on the diagonal. In Kn, each vertex is adjacent to any other vertices. So the degree of any vertex is n-1. So you can see on the diagonal, they are all n-1. And other entries, because if you take any two arbitrary distinct vertices I and j, because I is adjacent to j, so we have -1 for other entries which are not on the diagonal. Okay, now I'm going to define the number 5 of matrix associated to a graph, which is degree matrix. suppose that gamma is a graph, right? And if the vertex set is x1, x2, xn, so we have n vertices. The degree matrix of gamma is n times n matrix. So rows and columns are indexed by vertices of gamma, and we can denote by this matrix. It's a diagonal matrix. So all entries which are not on the diagonal is zero. Now for the diagonal, if you look at here, is for x1, 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 x1. So the first entry on the diagonal is d1. d1 means the degree of vertex xi. And similarly, for the second entry on the diagonal, we have d2 is the degree of vertex x2. And similarly, d3, di, and until dn. dn is the degree of vertex xn. This is the degree matrix. For example, if you see the path Pn, right? So the entries on the diagonal, the degree of 1 is 1. The degree of 2, 3, 4 until n minus 1, they are all 2. But the degree of n is again 1. So this is the diagonal matrix for degree matrix of a path Pn. And similarly for cycle, you know, for the cycle, the degree of any vertex x2, so that's the just a diagonal matrix which all entries on the diagonal are 2. For complete graph Kn, again we have n minus 1 on the diagonal because the degree of any vertex is n minus 1 because it's a regular. Now, it's interesting to give a relation between Laplacian matrix and adjacency matrix. So the degree degree matrix plays an important role to give this relation. So this is the relation for the Laplacian matrix and adjacency matrix. You can see that the Laplacian matrix of a gamma is the degree matrix of gamma minus the adjacency matrix of gamma. For example, if you see this graph gamma, so we can compute the Laplacian matrix directly by the definition. So you can see is a just definition, Laplacian matrix through the definition. For example, here the diagonal, on the first entry on the diagonal is 3. 3 is the degree of 1. Degree of 1 is 3. Now for example, for 1, you know, we have an edge between 4 and 1. So we have to put minus 1 here. Now, if you compute the degree matrix is we have 6 vertices, so is the 6 times 6 diagonal matrix. On the diagonal, you can see again degree of 1, degree of 2, 3, 4, 5, 6. So we have 3, 1, 2, 2, 4, 2. Is the same as diagonal of a Laplacian matrix. Now here is the adjacency matrix. If you see the adjacency matrix, now the difference between the degree matrix and the adjacency matrix is the Laplacian. So we have 2 ways to compute Laplacian matrix. the first way is to find the Laplacian matrix in a direct way by definition. And the second ways, which is a little bit maybe better, is that if you have adjacency matrix of a graph, so you need to just compute the degree matrix of a graph, and the difference between degree matrix and adjacency matrix is the Laplacian matrix. Another relation between the Laplacian matrix and incidence matrix. This is very interesting theorem to see that if we have a graph, of course, if a graph is directed or is not directed, we may put arbitrary direction on a graph. So if we have n vertices and m edges, and if Q of gamma is the incidence matrix, so the Laplacian matrix is the multiplication of incidence matrix and transpose of incidence matrix. So if we have the incidence matrix, again, we can compute the Laplacian matrix. For example, look at this graph, gamma, right? To find the incidence matrix, we may put just any direction. So I put arbitrary direction for graph gamma. Look at here. This is, we just put some directions. Now here is the incidence matrix. You know, we have 6 vertices and 7 edges. So the incidence matrix is 6 times 7 matrix, right? Look at here, for example, for in column related to edge E4. E4 is an edge from vertex 4 to 5. So look at here, A4, we have to put 1 from vertex 4 and minus 1 from vertex 5 here. So that's the incidence matrix. Now, if we multiplication of incidence matrix with the transpose of this matrix, then we will get the Laplacian matrix. So we have two, of course, three ways for finding Laplacian matrix. The first way is direct way by definition. The second using adjacency matrix and degree matrix. And the third one is using the incidence matrix. Now, here is another kind of Laplacian matrix, which is signless Laplacian matrix. So as I mentioned, so the Laplacian matrix is the Laplacian matrix is the just the difference between degree matrix and adjacency matrix. So the Laplacian matrix is the degree matrix minus the adjacency matrix. So if we replace minus by plus, then we get another matrix, which is signless Laplacian matrix. So the signless Laplacian matrix is the sum of degree matrix and adjacency matrix. So the difference between Laplacian matrix and signless Laplacian matrix is that in Laplacian matrix we have the difference, but here for signless we have the addition of two matrices. In other words, if we replace or minus 1 in Laplacian matrix by 1, we can get the signless Laplacian matrix. So, for example, if you take the cyclic group of order, this is the degree matrix. We have on the diagonal or R2, and that's the adjacency matrix, right? Now here is the Laplacian matrix. That's the just degree matrix of cycle of length n minus adjacency. Now, and on the right, we have signless Laplacian matrix, which is the addition of just we can add the degree matrix and adjacency matrix, or equivalently, you can see if we replace minus or minus one by one, we can get the signless Laplacian matrix. And also here another example for complete graph Kn, right? So this is the Laplacian matrix, right? And this one is the signless Laplacian matrix. So all minus one just replaced replaced by one. Now, the number 7 of matrix associated to a graph is distance matrix. Distance matrix is defined the following. So you can see here. So what happened?
Yeah, it's okay. I'm sorry.
Is that okay?
Yeah, I lost my connection.
All right.
Sorry.
Okay. Now, that's the distance matrix. So the rows and columns are indexed by vertices 1 to n. So if you take rows I, which is for vertex I, and column j for vertex j, so the enteras ij is the distance, is dij is the distance between vertex I and vertex j, right? And you can see that if you see the enteras on the diagonal are all 0, because the distance between any vertex to itself is 0, because we don't have any loop. We are talking about the simple graph. So the enteras ij is the distance between vertex I and vertex j, and that's the length of shortest path between vertices I and j. And that's the reason that we assume that the graph is connected. Now, as example, for P4, so we have 4 by 4 matrix, and here is the for example, first row, we have the distance between vertex 1 and 1, which is 0. The distance between vertex 1 and 2 is 1. The distance between 1 and 3 is 2, because we have 1, 2, 2, 2, 2, 3. And the distance between 1 and 4 is 3, right? Because we have a path of length 3. And so here is the distance matrix for P4. Now, if we have gamma is this graph, so you can see that, for example, in the second row, so the distance between 2 and 1, 2 and 1 is 1, 2 and 2 is 3, 2 and 3, 2 and 3, you know, the distance between 2 and 3 is 2, right? Because we have to go from 2 to 1, 1 to 3. You know, we may have pass more than length 2. For example, we can just see the pass from 2 to 1, 1 to 4, 4 to 3. Here is of length 3, but the shortest one is 2. 2, 4. 2, 4 is 1 because 2 is adjacent to 4, and 2, 5. 2, 5 is also 2 because we have some pass between 2 and 4, 2 and 5, but the shortest length is 2. So that's the distance matrix. For complete graph, Kn, we know that any of 2 vertices are adjacent, so the degree of any 2 distinct vertices is 1. And on the diagonal is 0 because the distance between any vertex to itself is 0. So this is the distance matrix, and you can see that we can just display as the difference between 2 matrices. J and N is the N times N matrix with all entries are 1, and I and N is the identity matrix, which we have 1 on the diagonal and 0 other vertices. Now, the last matrix associated to a graph is the H Laplacian matrix. You know, we have already Laplacian matrix, so we may put Laplacian matrix is just vertex Laplacian matrix. Now here is H Laplacian matrix. So the definition is the following. Suppose that gamma is a directed graph, so we have a direction here. And we have n vertices, 1, 2, up to n, and m edges, E1, E2, and En. The H Laplacian matrix of gamma, we may denote it by K of gamma is M times M matrix. You can see here is a different size. Is M times M. M is the number of edges. So M times M matrix. So in H Laplacian matrix, the rows and columns are indexed by edges, right? So on the rows we have E1, E2, En, so M edges for the rows, and similarly M edges for the column. Now, what's the entries of Ij? So if you take HEI for row I and HEJ for row J, if we put Kij for the entries, now we can define Kij here. So the first case is that if I is J, it means on the diagonal, if I is J, the Kij is 2. So it means that all entries on the diagonal are 2. Now, if I is not equal to J, so we have 2 distinct edges, EI and EJ. Now, we have also 2 more cases. The first case for distinct edges, EI and EJ, is that EI and EJ has no intersection. So in this case, put 0 for the entry. But if EI and EJ has intersection, if it has intersection, again, we have 2 subcases. the case one is that EI and EJ, right? They have intersection, but the direction of EI and EJ is one of these two cases. You know, it means that from intersection point, the the direction just going out, or here in the second sub case is that the direction of EI and EJ coming to the intersection point. So in this case, if for vertices EI and EJ, which has intersection, if the situation of EI and EJ, if one of these two cases, in case one, we will put 1. And in the second case, if the direction is one of these two cases, you know, the direction of EI is going out, but for EJ is coming in, right? Or just EI coming in and EJ going out. If we have one of these two cases, then we can put EI and EJ, the interest is -1. So in Laplace, in H Laplacian matrix, so we have 4 values for the interest: 2, 0, 1, and -1. So as an example, suppose that we have a graph gamma with 6 vertices, right? And 7 edges. We have 6 vertices and 7 edges. So the H Laplacian matrix is 7 by 7 matrix, and as you can see, the rows and columns are indexed by these 7 edges. So we have 7 rows for just associated to edges E1, E2 until E7, and similarly 7 columns for these edges. Now look at E1, E1, E2, E2. On the diagonal, by definition, we have 2. Now in the first row, E1, E2. Look at E1, E2. E1 and E2, they have intersection, so it's not 0. But you can see E1 and E2 are both going out from the intersection. So that's the case 1 of these positions. So we have 1, you know. Look at here, if we have 2 edges going out or coming in to the intersection point, so we can put 1. So here the entries E1, E2, we have 1. How about E1, E3? E1, E3. E1, E3, you know, E1 from the intersection point, which is vertex 1, E1 is going out and E3 coming in. So that's in the second case, we have to put -1. E1, E4. E1, E4, we have again in the second case, E1 coming down and E4 going out from the intersection point. So we have again -1. Now look at E1, E5. E1 and E5, there is no intersection, so it's 0. E1, E6, again, there is no intersection and it's 0. E1 and E7, again, it's 0. So by the same method, we can compute all entries on the Laplacian matrix. Now, as you remember, I gave a relation between Laplacian matrix and incidence matrix. For the Laplacian matrix was the multiplication of incidence matrix and the transpose of incidence matrix. Now here is another relation for the H Laplacian matrix. So the H Laplacian matrix of gamma is the transpose of incidence matrix times the incidence matrix. You know, in the Laplacian matrix, the transpose comes in the second matrix, but here, and if you see this, the size of both matrix, so the transpose inverse, the transpose of graph inside this matrix of gamma here is m times n, because we have m edges and n verts. So here is m times n, and the inside this matrix is n times m. So the multiplication of these two matrices is m times m matrices, as the definition for the H Laplacian matrix. For example, in the previous example, if we compute the transpose of inside this matrix, so this is the transpose, and the second is the inside this matrix, then we can get the just H Laplacian matrix. Now, let me give about some application of these matrices, and just define different spectrums and energies for the given matrices. So as I mentioned, for the Laplacian matrix, so the Laplacian matrix we may compute by the difference, by the just, you know, was the difference between degree matrix and adjacency matrix. And you know, here, because the Laplacian matrix is n times n matrix and the matrix is symmetric, so we have n eigen, n real eigenvalues. So if lambda 1, lambda 2, and lambda n is all eigenvalues of the Laplacian matrix, so you may put Laplacian matrix as a vertex Laplacian matrix. So the vertex Laplacian matrix we may denote by L of gamma, and for the H Laplacian matrix we may denote by K of gamma. So for the Laplacian matrix we have n eigenvalues. The Laplacian spectrum is set of all eigenvalues of Laplacian matrix. So we'll have n eigenvalues. Of course, it depends on the multiplicity. So if we have lambda 1 with multiplicity something, so we may put lambda 1 to the multiplicity degree. Now, the Laplacian energy. The Laplacian energy is the sum of absolute values of all eigenvalues of Laplacian matrix. So this is another energy, because the energy which I have already mentioned, it was the sum of all eigenvalues for the adjacency matrix. Now here is the sum of all absolute values of eigenvalues of Laplacian matrix. So we may denote by Laplacian energy by LE of gamma. Similarly, for signless Laplacian matrix, so the signless Laplacian matrix is the sum of degree matrix and adjacency matrix, and again is n times matrix. And we have also here n real eigenvalues for the signless Laplacian matrix, right? So the signless Laplacian spectrum is again the set of all eigenvalues of signless Laplacian matrix. So we may denote by SL a spectrum of gamma. And we may have also the signless Laplacian energy. So this is the third kind of energy, which is sum of absolute values of all eigenvalues of signless Laplacian matrix. For the distance matrix, so distance matrix, we have n times m matrix, right? And as this is the symmetric matrix, so again we have n eigenvalue, n real eigenvalues for the distance matrix of gamma. So we may introduce distance spectrum. Distance spectrum we may denote by d aspect of gamma is again the set of all eigenvalues of distance matrix. And distance energy, this is the number 4 of energy. So that's another energy which is associated to distance matrix, and that's the sum of absolute values of all eigenvalues of distance matrix. Now for H Laplacian matrix. H Laplacian matrix, which I defined here, is M times M matrix, right? And so we may compute by direct way, or we can just we can compute by using the incidence matrix, right? So that's the transpose of incidence matrix times incidence matrix. So we have M times M matrix. So we have M eigenvalues because it's a M times M matrix, right? And that's the symmetric matrix. So we have M real eigenvalues. So if eigenvalues of the H Laplacian matrix is lambda 1, lambda 2 until lambda m, so the H Laplacian spectrum, the H Laplacian spectrum of gamma is the set of all eigenvalues of set of all eigenvalues of H Laplacian matrix. And here is another energy, which is H Laplacian energy. So H Laplacian energy of gamma is the sum of all absolute values of all eigenvalues of the H Laplacian matrix. Right, so you can see we have different kinds of spectrum and different kinds of energies. Now, let me just start with an example on algebraic graph. Now, look at here. Suppose that D8 is a dihedral group of order 8. And gamma D8 is the non-commuting graph of D8. You know, this is example and for one of algebraic graph, so we may have the same thing for just other algebraic graphs. This is as an example. So we have dihedral group of order 8, so that's the presentation. So dihedral of order 8 can be generated by two elements, A and B. A has order 4, B is an element of order 2, and we have a relation BAB is A inverse. And we have 8 elements, so we have identity A square A cube, and BAB A cube B, and A square B and A cube B. So we have 8 elements here. You know that the center of dihedral group of order 8 consists of identity and A square. So for the non-commuting graph, we know that the vertex set is the set of all non-central elements. So we have to remove identity and A square from the vertex set. So we will have six elements as a vertex set. So we have A cube, B, AB, A square B, and A cube B. Now here is non-commuting graph of the dihedral group of order 8, right? So you can see A cannot be adjacent to A cube because A and A cube are commute, because A times A cube is A to the 4 is identity, and A to the A cube times A is again. So A and A cube are commute, so we don't have any H. But we have H between A and B, because A and B are not commute. And also we have H's from A to A square B, A to A cube B, and A to the AB. So the degree of A is 4. Similarly, for A cube, we have 4 H's involving A cube. We have H's from A cube to B, because A cube and B are not commute. A cube and A square B, A cube and A cube B, and A cube A B. And here are some other edges for vertex B, AB, A square B, and A cube B. You know, here B and A square B, we don't have H between B and A square B, because A square B times B is A square, B square is A square. And also B times A square B, because A square is in the center. So we can just commute A square B, again we will get A square. So since B and A square B are commute, we don't have any H between them. And similarly for AB and A cube B. Here is the degree of all vertices. You know, the non-commuting graph for dihedral group of order 8 is a 4 regular graph. So degree of any of these 6 vertices are 4. Now, let me start with the matrices which I mentioned today. The first one, adjacency matrix. Adjacency matrix for dihedral group of order 8. This is the adjacency matrix. We have 6 vertices. So the adjacency matrix is 6 times 6 matrix. And you can see here, for example, A and A is 0 because we don't have H between them. A and A cube is also 0 because A and A cube commute. A and B is 1 because A is adjacent to B. And similarly, A is adjacent to AB. We have 1. A adjacent to A cube B. We also have 1. A is adjacent to A cube B. We have also 1. And you can see that's all enterized for the adjacency matrix. So how about the degree matrix? degree matrix, we know the degree of any of these 6 vertices are 4. So the degree matrix is 6 times 6 matrix, diagonal matrix, and the entries on the diagonal are all 4. So that's the degree matrix. Now, how about the eigenvalues of adjacency matrix? If we compute the eigenvalues for the adjacency matrix of non-commuting graph of dihedral group of order 8, we have 3 zero eigenvalues. So lambda 1, lambda 2, and lambda 3 are 0. And we have 2 eigenvalues equal to -2. So the lambda 4 and lambda 5 are -2. And the last eigenvalue is 4. Now, the spectrum of this graph of the adjacency matrix, so is the set of, so we have 0 with multiplicity 3, -2 with multiplicity 2, and 4 with multiplicity 1. That's the spectrum for the dihedral group of order 8. Now, how about the energy? So the energy of just non-commuting graph is the sum of all eigenvalues of the adjacency matrix. So we have 3 zeros and plus 2 absolute value of -2 plus 1, 4. So the energy of non-commuting graph of dihedral group of order 8 is 8. Now, how about the Laplacian matrix? The Laplacian matrix, we may use, because we have already computed adjacency matrix and degree matrix, so we can use this not direct way, just by using the degree matrix and adjacency matrix for the Laplacian matrix of non-commuting graph of dihedral group of order 8. So it's the degree matrix minus the adjacency matrix. So if we just compute this difference, we will get the Laplacian matrix here. So here is the Laplacian matrix for non-commuting graph of dihedral group of order 8. Now, how about the eigenvalues? The eigenvalues of the Laplacian matrix, we have 6 by 6 matrix, so we have 6 eigenvalues here. The eigenvalues of Laplacian matrix of non-commuting graph of D8, so we have 0, 1, 0, we have 3, 4, so mu2, mu3, and mu4 are 4, and 2, 6, so mu5 and mu6 are both 6. So the Laplacian spectrum for the non-commuting graph of dihedral group of order 8, so we have 0 with multiplicity 1, we have 4 with multiplicity 3, and 6 with multiplicity 2. Now, how about the Laplacian energy? So if we add the if we compute the sum of absolute values of all eigenvalues of the Laplacian matrix, so we will get 24, because we have 3 times 4 is 12, plus 2 times 6 is 12. 12 plus 12 is 24. That's the Laplacian energy. Now, how about signless Laplacian matrix? Signless Laplacian matrix, we have, here we can use again by just by using the adjacency matrix and degree matrix. So the sum of degree matrix and adjacency matrix of non-commuting graph of D8, we can get the signless Laplacian matrix. So here is the signless Laplacian matrix. So the signless Laplacian matrix is 6 times 6 matrix. On the diagonal, we have 4. And you can see, just if you compare the signless Laplacian matrix with the Laplacian matrix, you just replace -1 by 1. The eigenvalues of signless Laplacian matrix of non-commuting graph of D8. So we have 8 as the first eigenvalues. We have 2 eigenvalues equal to 2. So lambda 2 and lambda 3 are 2. And we have 3 eigenvalues equal to 4. So lambda 4, lambda 5, and lambda 6 are 4. The spectrum of signless Laplacian matrix of non-commuting graph of D8. So we have 8 with multiplicity 1. We have 2 with multiplicity 2, and 4 with multiplicity 3. Now the eigenvalues, we have again here 24. We have 8, 1, 8. We have 2, 2 is 4, and 3, 4 is 12. So 8 plus 4 plus 12 is 24. That's the signless Laplacian energy of graph. Now, how about the distance matrix? The distance matrix of this graph. The distance matrix, for example, in the first column, we have, the distance between A and A is 0 because we don't have any loop. The distance between A cube and A, A cube and A are commute, so we don't have any edge between A3 and A cube and A. But the distance is 2. Let me show you again the graph. Look at this graph. The distance between A and A cube is 2 because we can choose the path from A to B, B to A cube. So the path is this is the shortest path, and the shortest length is 2. So the distance between A and A cube is 2. Now, how about the distance between, for example, A and B? A and B, we have an edge, so the distance is 1. How about the B and A cube B? B and A cube B, the distance is 2 because they are not, right? But we can choose the path from B to A cube and A cube to A square B. So distance between B and A square B is 2. But the distance between BA, BAQ, B, AB, BAQ, B are 1. And the same thing, we can compute the distance between any of these, any two vertices. So this is the distance matrix for non-commuting graph of the 8. We have 6 times matrix. Now the eigenvalues of distance matrix. So this is the eigenvalues. We have 2 eigenvalues equal to 0. So lambda 1 and lambda 2 are 0. And lambda 3 is 6. Lambda 4 and lambda 5 are -2, and also lambda 6. So we have 0 with multiplicity 2, 6 with multiplicity 1, and -2 with multiplicity 3. So this is the distance spectrum of non-commuting graph of dihedral group of order 8. Now, how about the distance energy? The distance energy of the graph is 12, because we have 2 zeros. 1, 6 is 6, 3, absolute values of -2 is 2. So 3 times 2 is 6, plus 6 is 12. So the distance energy of this graph is 12. Let me give some more properties about the distance matrix. Distance matrix is very important in trees, because if you take a tree, in tree, you know, for any first of all, we know that the tree is connected, of course, and we don't have any cycle. In tree, if you take any 2 arbitrary vertices, we have a path, and the path is unique. So we have only one path from any of 2 vertices. So the distance between any of 2 vertices is the length of the path. If you consider the distance matrix of a tree, suppose that tree is a graph with n vertices. So the distance matrix of a tree is n times tree matrix. Now, one of important properties of distance matrix for a tree is that if you compute the determinant of distance matrix for a given tree, so the determinant of distance matrix for a tree of n vertices. So the values of determinant for distance matrix of any arbitrary tree with n vertices are the same. So it means that if, for example, if we have a tree with four vertices, so we may have P, the path P4 is a tree. So the determinant of the distance matrix of P4 is equal to the determinant of distance matrix of another tree with 4 vertices. For example, K1 tree star from 1, K1, 1 goes to 3. So that's also a tree. So any any two trees with n vertices, the determinant of the distance matrix are the same. This is very interesting property of distance matrix. All right. Now, if we put a direction for the non-commuting graph of dihedral group of order 8, for example, if we put this direction, so we have here we have 12 edges. You know, we have 6 vertices and we have 12 edges. I showed the direction of any edge. For example, E1 is an edge from A to B. E2 is an edge from A to AB. E3 is an edge from AQB to A. E4 is an edge from AB to A. E5 is an edge from B to A, Q, and so on. So we have 12 edges. Now, how about the edge Laplacian matrix? Of course, we have two ways to compute the edge Laplacian matrix. The first way is to compute exactly by definition. So we can compute directly through the definition of edge Laplacian matrix. Or secondly, we may use the inside this matrix and the formula which I have given for the edge Laplacian matrix, which was the transpose of inside this matrix times the incidence matrix, right? Now here is a direct way. Of course, I don't have time to complete all entries. Just let me explain for rows, for example, 1 and 2. For rows 1, look at E1. So, as you know, by definition of the edge Laplacian matrix, right? So, on the diagonal, we always have 2. So, E1 and E1 is 2. Now, E1 and E2. Look at E1 and E2. E1 is from A to B, and E2 is from A to AB. So E1 and A2 both are going out from the intersection point A. So we have to put 1. E1 and E3. E1 and E3. You know, E1 is from A to B, E3 from AQB to A. So you know, here is the second case. So the entry E1 and E3 is -1. E1, E4. E1 and E4, again, we will have -1. E1 and E5. E1 and E5, again, -1, right? E1 and E6. E1 and E6. There is no intersection. So E1 and E6 is 0. E1 and E7. E7, again, 0, because there is no intersection. E1 and E9. E1 and E9, they have intersection B, and because they are coming in, so the entry E1 and E9 is 1. E1 and E10 is 0 because there is no intersection. E1 and E11 is 0. E1 and E12 again is 1 because B is the intersection. and both are coming in. So, here is the first row which I explained about the entry. So similarly for E2, E3, so you can compute the entries of the H Laplacian matrix. So it's 12 by 12 matrix. So then you have to compute the eigenvalues. So we will have 12 eigenvalues, right? The spectrum of H Laplacian matrix is the set of all eigenvalues. So we have to check that they are all distinct, or maybe they have some multiplicities. And the H Laplacian energy is the sum of absolute values of all eigenvalues of H Laplacian matrix. So we have to add the absolute values of 12 eigenvalues. Right. Now, let me, I have already mentioned 4 projects. Now, I would like to give 2 more projects here. Project number 5. Similar as to this example, in this example, for non-commuting graph of dihedral group of order 8, I computed all matrices, all just a spectrum eigenvalues of these matrices, energy of these matrices, right? So the project number 5, find all such matrices as this example for non-commuting graph, of dihedral group of order 2 times n. I computed for non-commuting graph of dihedral group of order 8. Now, what are these matrices for non-commuting graph of dihedral group of order 2 times n? And you have to determine the matrix exactly, each of these matrices. So it depends on n. For example, if you look, if n is even, so the number of vertices is 2n minus 2, because if n is even, then the center of the dihedral group of order 2 times n consists of 2 elements, identity and a to the n over 2. So we have to remove the center from the elements of the dihedral group of order 2 times n. So we will get 2n minus 2 vertices. If n is odd, then the vertex consists of only identity elements. So the number of vertices is 2n minus 1. So for each case, you have to see that what's the size of matrix. So if n is even, the size of most of matrices like adjacency matrix, Laplacian matrix, distance matrix is 2n minus 2. But if n is odd, then the size of these matrices is 2n minus 1 by 2n minus 1. And then you have to compute eigenvalues for each of these matrices. And finally, to determine the energy. So the project number 5 is to compute all of these matrices for a non-commuting graph of dihedral group of order 2 times n. Now, the the project number 6. The project number 6 is that, again, we ask you to find all these matrices, eigenvalues of these matrices and the energy for non-coprime graph of, again, dihedral group of order 2 times p to the n, for p is an odd prime. You know, the non-coprime graph, if you remember, for the non-coprime graph, the vertex set is the set of all elements of the group. So if you take dihedral group of order 2 times p to the n, so you will have 2 p to the n vertices. Now, if you have 2 vertices, so we say that if we have, for example, 2 vertices, x and y, we can say that x is adjacent to y in non-coprime graph if their orders, order of x and order of y, are coprime, or non-coprime are not coprime. You know, in coprime graph, if you take any of 2 vertices, right, any of 2 vertices, they must be coprime. Non-coprime means that they are not coprime, so they will have just a divisor except one. So for the non-coprime graph of this group of order, dihedral group of order 2 times p to the n, you have to find, first of all, determine the graph structure for non-coprime graph, and then compute all such matrices and eigenvalues of these matrices and also energy of these matrices. Right. Let me give another example. This is an easy example for a symmetric group of order 6. I'm going to determine the coprime graph. You know, in project number 6, I mentioned non-coprime, but here is coprime. It means that 2 vertices are adjacent if their orders are coprime. So suppose that S3 is a symmetric group of order 6. So we have 6 vertices here. Now, I mentioned some questions to find each of them by y. First one, I asked to draw coprime graph of S3. The second is to determine coprime degree of S3. Coprime degree. And third one is to find adjacency matrix for the coprime graph of S3. And number 4 is to determine energy of coprime graph of S3. And similarly, find Laplacian matrix for coprime graph of S3 and Laplacian energy of this. And also, we may continue to find some for some other matrices, but here is number 5. I mentioned that find relations between coprime degree, coprime graph an adjacency and Laplacian matrix of co-prime graph for S3. So it's interesting to give some relations between all of things which up to now we just mentioned in the series of lectures about the probability, about the graph, about adjacency matrix, Laplacian matrix, and so on. Now, let me give a solution just a step by step. For number one is to draw co-prime graph. So you can see we have 6 elements. The order of identity is 1. The orders of 1, 2, 1, 3, and 2, 3 are 2. And for 1, 2, 3, and 1, 3, 2 are 3. Now here is the co-prime graph for S3. As you see, identity is adjacent to each of other vertices. So identity is adjacent to 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. But here we don't have any edge between 1, 2, 1, 3, and 2, 3 because they have order 2 and they are not co-prime. And similarly, we don't have any edge between 1, 2, 3 and 1, 3, 2 because they are also are not co-prime. So the greatest common divisor of, for example, order of 1, 2, 3 and 1, 3, 2 is 3. But we have edge between any of elements of order 2 to any of orders of order 3. So this is the graph, the co-prime graph of S3. The number of edges is 11. So you can just count the number of edges. So we have 11 edges for co-prime graph. Now, how about the co-prime degree? Co-prime degree is the number of pairs X and Y which are co-prime, their orders are co-prime, divided by order of G square. So in lecture 2, I think I computed the co-prime degree for S3 and it was 23/36. Right. Now, the adjacency matrix of co-prime graph of S3. So for co-prime graph, you know, we have 6 vertices, and by definition of adjacency matrix, we have 0 on the diagonal, right? And for any of 2 vertices, we have to see if there is an edge between them, we can put 1, otherwise we will put 0. For example, you know, 1, 2, and 1, 2 is 0, 1, 2, and 1, 2, and identity is 1, 1, 2, and 1, 2 is 0, 1, 2, and 1, 3 is 0 because they have the same order and they are not co-prime. 1, 2, 2, 3 is again 0, but 1, 2, 1, 2, 3 is 1 because we have an edge between 1, 2, and 1, 2, 3. And similarly for 1, 2, 1, 3, 2 is 1. So that's the adjacency matrix. Now, the next one I ask about the eigenvalues of adjacency matrix of co-prime graph of S3. So I computed by online just software to compute the eigenvalues. You can easily find the eigenvalues. So we have 3 zeros and the other three eigenvalues is minus 2.271, minus 13341, and 3.612. So the energy of co-prime graph is 7.224. So we have to find the sum of absolute values of these 6 eigenvalues. Now, the Laplacian matrix. The Laplacian matrix for co-prime graph of S3. So, for the Laplacian matrix, as you can see on the diagonal, is the degree of related vertex, right? For example, on the first entry on the diagonal is 5, because the degree of identity is 5. Let me again see. You know, the degree of identity is 5, because identity is adjacent to any all other vertices. But the degree of 1, 2, 1, 3, and 2, 3, the degree is 3. The degree of 1, 2, 3, and 1, 3, 2 is 4. Now, for the other entries for the Laplacian matrix of co-prime graph of S3, let me just see one of rows. For example, the second rows, E2, 1, 2, and E. 1, 2, and E, you know, 1, 2 is adjacent to identity. Since they are adjacent, so we have to put -1. But 1, 2, and 1, 3, we don't have edge, so we have to put 0. 1, 2, 2, 3, again 0. 1, 2, 1, 2, 3, we have an edge, so it's -1. And 1, 2, 1, 3, 2 is again -1, because we will have an edge. So this is the Laplacian matrix for co-prime graph of S3. Now, how about the eigenvalues? So I find the eigenvalues. This is the eigenvalues for the Laplacian matrix. So we have 0, 1, 0, 2, 3, 1 eigenvalue equal to 4, and 2 eigenvalues equal to 6. So we have 0 with multiplicity 1, 3 with multiplicity 2, 4 with multiplicity 1, and 6 with multiplicity 2. So if we add the absolute values of these eigenvalues, so the Laplacian energy is 22. Now, the last part, which is a little bit interested to combine all together, is that I mentioned when I introduce co-prime graph, I give a relation between the number of edges of co-prime graph and co-prime degree. So for the S3, the number of edges of co-prime graph is a half of order of S3 squared times the co-prime degree of S3 minus 1, right? So look at here. Here, the co-prime degree of S3. So what's the definition of co-prime? The co-prime degree of S3 is that we have to count the number of pairs which have co-prime orders, right? if we have co-prime orders in adjacency matrix, take two vertices in adjacency matrix. So if the entry of these two vertices in adjacency matrix is 1 if they have co-prime order, and is 0 if they have not co-prime order. So we can count the number of pairs through the adjacency matrix. So look at adjacency matrix of co-prime graph of S3. So what's the number of ones if you add all entries of the adjacency matrix? You know, in adjacency matrix we have some zeros and we have some ones. What's the number of ones? Is that true? The number of ones is the number of pairs which they have co-prime order, right? So the probability, the co-prime degree of S3 we can compute by, right, by we can compute by finding the summation of all entries in adjacency matrix. So the sum of all entries in adjacency matrix divide by order of S3 square is exactly the co-prime degree. Because if you see the co-prime degree, the co-prime degree is the number of pairs divided by order of, if you take any group G, so the co-prime degree of G is the number of pairs having co-prime orders divided by order of G square, right? So this summation is exactly the number of pairs, right? So the number of pairs times the order of S3 square is, you know, order of S3 square times the co-prime degree is exactly the number of pairs. So this is the relation between the number of edges and the sum of all entries in adjacency matrix. So by this equation, we can see that we can get this formula that the sum of all entries in adjacency matrix is order of S3 square times the co-prime degree minus 1, right? And also we can see that the number of edges in co-prime graph is the half of the, you know, here is the Laplacian matrix. So if you add, look at the Laplacian matrix. In Laplacian matrix, what's the entry on the diagonal is the degree of vertices. So the sum of all entries on the diagonal is the sum of degrees of all vertices. But you know, we have the formula. If you find the sum of all degrees in a graph is 2 times the number of edges, right? So the number of edges in co-prime graph of S3 is the half of the sum of all entries in the diagonal in Laplacian matrix. Because in Laplacian matrix, you know, in in the diagonal, you have the degrees of vertices, and the sum of degrees of all vertices is 2 times the number of edges. And here also you can see that the sum of all entries in the diagonals of Laplacian matrix is the order of S3 squared times co-prime degree minus 1. So this is very nice relations between the co-prime degree. You know, we can use this relation not only for co-prime degree, for any algebraic graphs, for the number of edges and the probability associated to that group, and the adjacency matrix, the sum of all entries in adjacency matrix, or the sum of all entries on the diagonal in Laplacian matrix. Right, now let me give some more research problems. Of course, each of them can be also one more project. The first thing is that give a relation between probability, number of edges, and the rank of incidence matrix. I gave a relation between the probability, number of edges, and adjacency matrix and Laplacian matrix. Now you can find a relation between these numbers, probability, number of edges, and the rank of incidence matrix. Now, the second question is to find a relation between energy of a graph and the relative probability, because we define just different kinds of probability. So for each probability, for example, for non-commuting graph, we have the commutativity degree, we define the non-commuting graph, we have energy. Now, the question is to find a relation between energy. You know, energy, of course, the first step, we can consider the energy of adjacency matrix, right? Now, in the second steps, you may consider other kinds of energies. So give a relation between energy of a graph and the probability. What we can say about these two, because energy is a just positive number, and the probability is also a number. So what we can give a relation between these two numbers. The probabilities is not integer, mostly is rational number, but the energy, of course, we may have energy of sometimes, because energy is the sum of absolute value of values of all eigenvalues. Sometimes is integer, and sometimes maybe is not integer. Depends on the eigenvalues. And the third question is that suppose that we have two graphs, G1 and G2, right? Now, if we have two groups, G1 and G2, and if we have isomorphism between two associated graphs, for example, you may consider non-commuting graph, co-prime graph, non-co-prime. So we have isomorphism between two graphs associated to group G1 and G2. Now, the question is that So is that G1 and G2 have the same probability? We have isomorphism between two graphs. So is that this isomorphism gives us the equality for the probability of these groups? Or how about the energy? Is that they have the same energy if these two graphs are isomorphism? The energy means energy for adjacency, or maybe some other kinds of energy like Laplacian energy and so on. So there are some sort of questions we can consider for each of graphs, each of algebraic graphs, which I mentioned, right? So it's very important to see that how is important the isomorphism between two graphs. Is the isomorphism between two graphs is more strong to preserve the equality between energies, between probabilities, and so on. And the last comment by myself is that it's very interesting to see that if you take any graph, I haven't mentioned here, but I just explain. If you have a graph, and if you consider any of matrices which I mentioned, of course, not except inside this matrix, because inside this matrix is not always a square matrix, and we have eigenvalues for only a square matrix, because for inside this matrix we may have some vertices and some edges which are not equal. So except inside this matrix, for other matrices, so if you find the eigenvalues of associated matrix, so we have two cases. The case one is that all eigenvalues of the associated matrix are integer. And the second case is that some of eigenvalues may or not, we may have some non-integer eigenvalues. So if all eigenvalues are integer, in this case, for example, for the adjacency matrix, they are very important as integer graph. So integer graph means all graphs which all eigenvalues are integer. Now, it's very important to classify all integer graphs. For example, for adjacency matrix, there is not just a complete classification, but they consider, for example, for Cayley graph, which of Cayley graph are integer graph, or which of we have to consider many kinds of graphs. For example, complete graph is integer graph because all eigenvalues are integers. But some of bipartite graphs are not integer, because in complete bipartite graphs we have two non-zero eigenvalues. So if we have complete bipartite graph K and M, so we have the square root m n and minus. So the square root m times n is not always integer, right? So it's very interesting to give a classification, or even you find in the family of graphs, you just determine all integer graphs. So this is another just comment which you can deal with algebraic graph, with probability which with expectora graph theory. Okay, thank you very much. So we may have 15 minutes for any questions and comments. Thank you very much indeed.
Okay, thank you very much, Professor.
Thank you.
Maybe any question? Yeah, that's really new for me. Maybe from Bu Yeni or from me.
Object.
Okay.
Sorry.
Oh, not yet. Okay. So yeah, maybe one question from me. I'm still thinking in your last research question, you try to compare two isomorphic graph and then what happened with the energy and then also the Laplacian energy, right? Maybe my question is when we have two graphs which are maybe they have same vertices and then they also have same energy, and then are there some properties that maybe they have the same for both graphs, or maybe if they have the same Laplacian energy, and then what is the implication if there are two graphs with same energy or same Laplacian energy? Maybe, yeah.
Yes, if we have two isomorphism graphs, in isomorphism between two graphs is, in isomorphism we have preserving edges and the degrees.
Yep.
So the
Yeah.
degrees. So you're right that they will have maybe the same adjacency matrix and the same Laplacian matrix, maybe just changing some rows or columns, but
Yep.
yeah, but they have the same energy. If we have isomorphism between two graphs, so obviously they have the same eigenvalues and consequently they have the same energy. Yeah, you're right. So it's the answer is very easy for this question.
Yeah. Maybe for the
But
next one. Yeah.
But it's very interesting. If you replace graphs with, for example, having the same probability, or sometimes you may just assume that if they have the same order, if we have two groups with the same order, in this case, what we can say about the energy and so on. Yeah, I think for the Laplacian matrix and for the adjacency matrix, they have the same matrix if we have isomorphism.
Okay. And can I ask one more?
Yes, of course.
Yeah. I'm still thinking for general graph with n vertices and then m edges. So the energy should be finite, right? Cannot be infinite. Can we count maybe the upper bound for the energy or for the Laplacian energy for general graph?
Yes, there is a upper bound for the energy of a graph in terms of the number of vertices and number of edges. it's something like I think root n times m minus 1 something. If you look in some books, there is an upper bound for that. Yes, there is. And the bond is also sharp because we may find some graph with the exact values of the upper bound. Yes, we have.
Okay. Yeah, that's just my curiosity.
Yes.
Yeah.
If you look the book graphs and matrices by Bapak. If you look this Bapak, if you look this, there's some lower and upper bounds for the energy. If you could not find, just you can let me know. I will send the exact upper bound for you.
I think I can because from UGM they subscribe for Springer. This one is Springer, right?
Yes, that's right. Yeah.
Should be able to download via our university.
Okay. In any case, if you got any problems, just you can let me know because I have PDF files, so
Okay.
I may send to you if you like.
Okay. Thank you very much. Yeah, I think. Any more question maybe?
From me, maybe.
Okay.
Yeah. Thank you, Professor Erfanian. Up to date until today, we have got a lot of new knowledge in this algebraic graph. And one question from me, it's also on still an algebraic graph, but in vice versa. It means that we start from like a graph, and then from this graph, we construct a new like structure. I have found, I have ever seen one definition, semi-group that is constructed from a graph, and I'm just want to know whether you work also in this case. I mean, this structure from constructed from a graph.
You know, if you define any algebraic graph, so you have to use the algebraic structure for definition of the graph. I mean, the definition for having an edge between them. So depending on your groups or your semi-groups, right? It's not always easy to find the graph structure because, for example, sometimes, for instance, you consider a complete graph K5, right? So you deleted three of edges in complete graph. So how you can just display this graph? Because if you delete three edges, so it depends on these three edges. Is there, they have intersection, or they are disjoint, or they are not disjoint? For this easy example, is not easy to display the graph structure exactly. So if you are not able to define, if you are not able to determine the graph structure, so one of my suggestions is that you may consider some special induced subgraph, because if you consider some induced subgraph, then you may just display this subgraph very easy, because maybe this subgraph is complete graph, maybe this subgraph is complete bipartite graph, right? Or something like that. Maybe it's a star graph. So it depends on the structure of the group or semi-group. It's very important. And one of the difficulties is that in semi-group, sometimes the semi-group is or semi-ring is infinite. And in this case, you will have infinite graph. And the determining the structure of infinite graph is much more difficult than the finite case, right? So I cannot give you the certain way for, because it depends on your graph, depends on the just your algebraic structure, definition of graph. That's all important to determine the graph. We have some graphs which are not more clear, and there are some open problems for the graph. For example, if you take non-committing graph, right? Non-committing graph for dihedral group is completely determined. Now, how about the symmetric group or alternating group? Up to now is not determined in general case. So we don't have any graph structure for even non-committing graph of symmetric group Sn for any n bigger than or equal to 3. You know, so sometimes it's very difficult to determine the graph structure. It depends on the problem which you deal with them. Maybe your graph is easy to find the graph structure, or sometimes it's difficult, right? So we cannot give a special way for any graph. For each graph, we have to consider and maybe just follow with the way which we can do it. Sometimes you cannot do anything, right? So it depends on your graph. So I cannot give you a certain way for your problem. We have to see your graph, your semi-group or semi-ring, and so on.
Thank you, Professor. Very clear.
Okay.
Okay. Thank you very much. Any more question maybe for the last one? Okay.
Yeah. Hi. Yeah. I would like to ask about the energy, yeah, because you said that the energy of the matrix is the sum of absolute value of this eigenvalue. Yeah. If the eigenvalue is not real, then the absolute is the norm, or what? Maybe.
Yes. Here, you know, we have, first of all, let me thank you for very important things which you mentioned for the energy. You know, in each matrix which I mentioned, all matrices associated to a graph is a symmetric matrix. If we have a symmetric matrix, so it's guaranteed that all eigenvalues are real. So that's very important. So it means that
because it's symmetric, yes. Because I didn't see that you mentioned about this is symmetric.
That's right. It's very. Thank you very much for reminding me. Yeah.
Okay. And you mentioned also about the use in the chemistry. What is the use of this energy for matrices?
You know, actually, the energy coming from chemistry. If you see the motivation of energy in graph, it's actually comes from the chemistry, because in chemistry, if you have, for example, molecule water H2O, we have two hydrogen and one oxygen, right? H2O. So here is a graph. So we have oxygen on the middle, and we have two edges for hydrogen. So it's a pass. It's a pass P3, right? But for hydrogen, in chemistry, they have energy between just combining oxygen and hydrogen, so it produces energy. So the amount of energy, the exact amount of energy is is very, very close to the energy which we have in graph theory, right? So the definition of energy actually coming from chemistry. So because they compute on the lab for the energy, and in the graph theory, they check that it's very close. So approximately with many good estimate, they are the same. So that's the motivation for the energy, right? So I think you may search in Google about the energy of a graph and give, of course, in Wikipedia, if you through the energy, they will give some details about how to define energy in graph theory by chemists, because they came from the some chemist to in graph theory. And we have some journals in mathematical chemistry, and mostly talking about the graph associated to some things in chemistry.
Okay, thank you. Thanks a lot. Yeah, I off the camera because to reduce the load of the connection.
Yeah,
Okay.
that's right. Yeah.
Okay. Okay.
Last week I had the same problem, because if your camera is active, so it means that the speed of internet is coming down. So yeah. I have the same problem.
Thank you. Interesting topic today.
Thank you very much.
Yeah, thank you very much. I also asked the same question. Why the name is energy? Oh, okay, that's really answer the question.
Yeah, I answered to Prof. So that's your answer for the name of energy. Energy comes from the chemistry.
Chemistry. Okay. I think that's the last question for our discussion. Again, thank you very much for Professor Ahmad Erfanian for sharing today. Yeah. And before we end this session, I think I would like to remind you that we will have one more again. So next Saturday at the same time, and 1 week after we will have Idul Adha, so we will have a break. And for the last one is 3 weeks from now.
Okay, thank you very much.
Yeah, thank you very much, everyone.
Participant.
Thank you very much.
Thank you. So see you next week. Thank you very much.
See you.
See you.
Thank you.
All right.
And bye-bye.
All right then.